Hi, today I'm going to be talking about static electricity and the forces between two charged objects. So with static electricity, we have reminded ourselves that charged objects, like objects repel each other. Oh man. And opposite objects attract. Opposites attract. So we have these two rules for how charges work with each other. If they're the same charge, they repel. If they're opposite charges, they attract. And I want to remind people that we only have two types of charges. We have positives and negatives. A lot of people want neutral to be a third type of charge, but neutral is not a third type of charge. What a neutral object is just something that has equal amounts of positives and negatives. So we actually only have two types of charge, but then we have this third state where you could have equal positives and negatives, which means it's neutral. So when we have two charged objects, we can talk about different things causing different forces between them too. So if I have a positive, and they're a certain distance away from each other, then they're going to exert a force on each other. They're like, so they're going to repel. So the one on the left is going to repel the one on the right, and the one on the right will repel the one on the left. One of the tricky things when we're talking about the forces between charges is that you always want to draw what this charge feels. We don't care about what this charge does to the other charge. We only draw what this charge is feeling. So this charge feels a push this way, because this one's pushing it that way. This charge feels a repel that way. So when you're drawing arrows, only draw what these things are feeling. So if you were this positive charge, what would you feel? And that's something that tricks people up. So be careful when you're drawing the forces that you're only drawing what each one is feeling. So if we have two charged objects a certain distance away, in this case they're the same charge, then the force between them, we can talk about that force in terms of Coulombs Law. And when we talked about this to start, we determined that the amount of force between two charged objects depends on how much charge is here, how much charge is here, and the distance between them. If we put it into mathematical terms, the force is, I'm going to ignore the K for now, Q1 is the charge on object 1. So how much charge on number 1? And the unit of that is a Coulomb, which Coulombs Law, same dude. So it is in coulombs. Am I spelling it right? Yeah. You can probably guess Q2, charge on number 2, in coulombs again. Number 2 in coulombs. All right. The K is a constant. And so the K is always just going to be the same number. It is 9 times 10 to the 9th. It's not that hard to remember, 9 times 10 to the 9. And the unit for K is a Newton meter squared over coulombs squared. Don't worry about the units. And this is on your equation sheet. So we've got Q1, Q2, K, and R is one of the sneaky things. Typically when we talk about distances, we might call it D or X. But here we're talking about R. And if you think about R in terms of distances, what pops into your head? Maybe radius? And this actually is talking about a radius. But it's not talking about a radius as though this were a circle. It's talking about a different radius. This R is the distance between the two objects. So distance between object number 1 and object number 2. The reason it's given the label R for radius is because of the symmetry of how the forces act on each other. So if I were to take a positive object and, there we go, put it at the center here. Now if I take another positive object and put it out here at a certain distance away, they would have a certain force between them. Now if I take this object and move it up here at that same distance away, that would have the same force. Likewise over here, same distance away, same force, and hopefully you're starting to get the sense of why we call it a radius. because the force is going to be the same between this object and an object placed on this circle, anywhere around that circle, it'll be the same. So that's technically why we call it R for radius. And so don't get tricked into thinking it's half this. It is the distance between the two charged objects. So that here is Coulomb's law. And another thing we need to think about is how that law means the forces change. So if I have something, let's just say an object plus q and an object plus q, a distance r away from each other. That means there's going to be a certain force between these two, and I'm not going to worry about the number. I'm just going to call it a certain force F. So this situation, there's a force between them. That's F strong. Now if I were to triple this charge, so this one becomes plus 3q, same distance away from this one, which is the same, what would happen to the force? So think it through, and then you can say, okay, if this charge tripled, that means this one is now 3 times bigger. If you're thinking the force is going to be 3 times bigger, you got it right. So if we triple one of the charges, then the force is going to triple. If we triple both charges, keeping the distance the same, then this will be 3 here, this will be 3 here, and be careful, 6, 9, 6, 9. Are these adding or multiplying? We are multiplying these, so it's 3 times 3. This will be 9 times the force. Likewise with distance. Suppose I go back to this situation, and I have a plus q, and I have another plus q, but now not to scale. I've 3 times the distance between them. So if they were this far apart, now it's 3 times that distance between them. So what is this going to do to the force between them? If you think about what we saw with our sticky tape experiment, the farther away the two objects are, the weaker the force between them. That's why R is in the bottom here. As R gets bigger, the force gets smaller. Now we're tripling the distance. So we're putting a little 3 in front of that R. So you might say, well, the force goes down by 1 over 3. But we've got a squared here. It's not 3r squared, it's 3r parentheses squared, which means that here the force is going to go down to 1/9. So you can just use Coulomb's law to figure out the size of different things, the size of the force for different objects at different distances. And this is actually a sea-level objective for static electricity, to be able to do this and say, okay, if these are 3r at this distance away, it's going to be F over 9. If you want to give yourself a little test, how about if I had a plus 4q, 2r away from a plus 3q? Give yourself that test. Can you figure out what would happen to the force? If this is F, what's going to happen here? So hit pause, give it a try. Did you hit pause? Okay. So here we've got the force is K times the first charge, 4q, times the second charge, 3q, over the distance squared. And remember, keep that in parentheses. So what do I have here? This is going to be KQQ over R squared. Let's bring all the numbers out. There's a 4 on top, there's a 3 on top, and there's a 2 squared on bottom, which gives me a 4 on the bottom. Doot, doot. So I say this is a factor of 3 times bigger. So this makes the force 4 times bigger. This makes the force 3 times bigger, but the distance makes the force 1/4 the size, which balances out this, which means we're just left with the 3 times bigger. So there is just the real quick basics of Coulomb's law, the force between two charged objects. The only other thing I want to remind you about is Newton's third law. So if you need to go back and study up Newton's third law, because that's going to tell you how this is going to interact with this. So if I have like a plus 3q, and a negative 15Q a certain distance away, how does the force of the negative 15 on the 3 compare to the force of the positive 3 on the negative 15? So that's your homework for this video, is making sure you know how to answer that question correctly. And for the answer, you should come find me. All right, that's the basics of Coulombs Law. Good job.